नमो श्री यतिराजाय विवेकानंद सुरये सच्चित सुख स्वरूपाय स्वामी नेतापहारिणे। स्वामी जी, माँ शारदा और श्री रामकृष्ण को हमार भक्तिपूर्ण प्रणाम। Revered Maharaj Nikhilasananda ji, Swami Vedanishtananda ji, all revered monks and distinguished guests, and my dear students. It's indeed my privilege to share few of my thoughts and particularly on ISRO and recent progress we have made in space technology to this audience. To talk something about Swamiji to this audience will be Suraj ko Deepak dikhana jaise. So I am not doing that, but what I can tell is that whenever in life we need some direction, we need to find a meaning of life, we normally take refuge to Vivekananda ji, Shri Ramakrishna and Gita. These are our inspiration throughout our life, and it is going to be in the generations to come. Now, the subject I have selected is science and Swami Vivekananda. Now, all of you know about that Swamiji was very much interested in science and technology. When actually he was the World Parliament of Religion, it was a world's Columbian exposition. It was an universal exposition where science, technology, philosophy, religion, literature, everything was displayed at his full strength and full glory. So in front of him was the glorious West with all his science and technology, and behind him was 5,000 years of spiritual knowledge of India. So that's the backdrop where he was. And he was regularly interacting with the scientists there. Actually, this slide I have put for just to get a glimpse of the scientist. He was very closely associated with him. But it's not limited. He was having very widespread influence on the science and scientists and technologists. The first one, whatever you are seeing, is Nikola Tesla. Actually, he was having a pavilion in World Parliament of Religion and that exposition. And he was very, very fond of Swami Vivekananda ji, and he also used to go there and meet him and discuss about science and technology. And you know, Tesla was the greatest inventor of that time. In all walks of life, like AC induction motor, X-ray imaging, then wireless control and wireless communication also he has initiated. So today, what we are talking about in our all satellite communication and even regular communications. And Swamiji discussed with him about mass energy equivalence, and Tesla started working on that. But he was not gone, he left in between. Then Einstein in 1905, he showed the mass energy equivalence, and that was a milestone in science. And next you are seeing right side, Sir J.C. Bose. Swamiji inspired the greatest of our minds, and they are then led the world throughout history. Sir J.C. Bose was, what we are using about his work is millimeter wave technologies. But he was in International Congress of Physics in Paris when Swamiji was also there. Where? And Swamiji attended that lecture of Sir J.C. Bose. And he was so much impressed with that. I'll read from his experts what he thought about it. Here in Paris, we have assembled the great of every land. Each proclaimed the glory of his country, servants will acclaim here, and its reverberation will glorify their countries. Among their fearless men gathered from all parts of the world, where is thy representative, O thou country of my birth? Out of this vast assembly of young men stood for thee one of thy heroic sons, whose words has electrified the audience and will thrill his countrymen. This is what he wrote about Sir J.C. Bose. And afterwards, they had a lot of interaction about millimeter wave generation and reception. Swamiji wanted that he takes patent of that, but somehow J.C. Bose thought that, okay, knowledge should be for everyone. It should not be for a patented, or it should not be restricted. So he was not interested in that. And about the Jamshedji Tata, you have already heard, he was inspired, and then IISc was formed. And I think he proposed Swamiji as to become the first director, but it didn't happen. And I think the history of science would have been different if it would have happened. IISc has got a great connection with ISRO. The third chairman of ISRO, Professor Satish Dhawan, was the director of IISc, and he was in experimental fluid dynamics lab. And since that time till today, we are working on nanoscience with IISc, and they have a great association with ISRO. So these are the stories of all these great minds who were inspired by Swamiji and then led India to a greater height. Now, what we are using most is probably Sir J.C. Bose's work. That I will come next. Can I go to the next? Yes. So here you are seeing visible spectrum. Now, before that I go there, let me ask you, how many of you is really enthralled by the universe? Mostly the answer will be everybody, whether he is a spiritual person or he is a scientist or he is a common man. Universe always inspired humanity. And you know what is the key to this universe? What we have in our hand to explore it? It's mostly the electromagnetic waves. And that too, you know our limitation. Our eyes can detect only a part of it, that is visible spectrum. And there are lot much beyond that, below that and above that, we cannot see it. Only with scientific instruments we can extend it. But still there is limitation, and this is the limitations of our sense organs. We cannot do, we try to explore the reality with the science, but the problem is everywhere we face a limit. Anyway, science gives us some ways to extend this. And electromagnetic spectrum, when it passes through atmosphere, in few frequencies, it gets attenuated. And few frequency, it goes through the atmosphere. So whatever goes through the atmosphere, we use it for communication. And wherever there is an absorption, we use that for our regular remote sensing. That is something we try to sense, that what is there in the atmosphere, what is there below Earth. So for those remote sensing purposes, we use them. Now, when we try to study sun or any stellar object, we try to take image at different frequency bands. Now, different frequency bands means from IR, infrared to terahertz, and in the other side, X-ray and gamma ray. So if we look at sun, this is a picture of sun and shown in different frequency bands. And it gives different information. Like if you are getting some picture in 550 nanometer, that will be corresponding to 5700 degrees centigrade. When you image it at 94 nanometer, this nanometer is the frequency what you are trying to see. It will give almost 6 lakhs degree temperature. So we make telescope and spectrometer. Spectrometer is another thing. It doesn't give a picture. It gives it is a graph by which you can see that, okay, in which frequency your kind of light, what is the amount of that frequency contained in that light. Okay, now I will go to our space technology, because this is what was requested, that okay, I need to share some of our recent exploration of the space technology. So before I go there, I have to tell you something as a background. That is, when we talk about Earth, what do? We have to send, see, Earth anyway we are here, so we can sense it, and that is called ground truth. And we send satellite to sense the Earth's atmosphere and the Earth as a planet. So they are put in different orbits. One of such orbit is low Earth orbit. Low Earth orbit is around 160 to 2000 kilometers, whatever is there, we call them low Earth orbit. Another we use for communication purposes. Now, communication purposes where you use, normally we need a geostationary type of satellite. That is around 36,000 above. So what happens if you put a satellite there, because of Earth's rotation, it illumines the one portion of it, and mostly we keep it in India. But now you know that communication satellites are being put in LEO orbit also. That is, if you have heard about OneWeb and Starlink, now they are trying to cover the whole globe with low Earth orbit satellites. And when you go to moon, we have to image moon also, no? So our Chandrayaan 1 was around 190 kilometer orbit, and Chandrayaan 2 orbiter, actually which is very less talked, but that is the best orbiter we have got, and it's the best in the world. And whenever we are going to Mars, we went on an elliptic orbit. Elliptic orbit means in one time it will be around 350 kilometer, and another time it will be in 71,000 kilometer. So that is the way planetary explorations are made. Sorry, you didn't change the slide. Yes. So all these orbits we need to know before we start exploring, because these are the places where we normally put our satellites or space probes. Now, you have already heard about Aditya L1, it is launched. Can you go to the next? It is having a strange orbit. It is not rotating around anything, but see, if you put some space object to study sun, what you do, Aditya's name is Aditya L1. L1 is a Lagrangian orbit. What does it mean is, if you have a two body or three body system, at certain point you will see that there is zero gravity, the gravitation cancels, and that is the point where you can put the satellite, show that you can have a stable image, and still, okay, depending on the three body system and its centrifugal forces, it will have a orbit that is called halo orbit. So this is where the Aditya L1 is going to be placed. Yes. So now I will go, see, before I go here, I will just try to, I will share you something about our space exploration, how it started. It started with Dr. Vikram Sarabhai, but that time India was needing more than the space exploration, where other countries are on space race. What India decided that, no, we are not going to have space race. What we want, that from space, we want to image Earth, we want to do communication, show that every person of India gets benefited out of it. So it's a societal benefit what we tried to have at the first phase of our space program. So one such is the communication program. Now, what does it mean by communication program is that we put geostationary satellite, and if you know about a program site, it was conducted in Gujarat and around. Initially we are not making satellites. We took the satellite from US and experimented, the huge experiment on satellite instructional television experiment what was done for education of Indian masses, and that was the biggest experiment of this sort in the world. And that started the Indian space program and communication program in particular. Now today you have communication satellites. See, if you today look at today's communication scenario, what do you see? You have mobile in your hand, but the place where there is no mobile, you have satellite, and wherever you are in a problem, like disaster on that condition, whatever communication infrastructure you put, it is going to fail. And that time you can immediately go and put a satellite infrastructure. So that is right now the social responsibility wise, that is a part of communication now. And another important fact is the telemedicine network. Now, when you are in a city, that is absolutely not a problem. You can go to hospitals. But when, there was a program that is in Leh Ladakh area where armies are there or the common persons are there, there was no hospital. So they have put telemedicine node there, and from the specialist sitting in some other place, they are able to guide the doctors who are sitting there. So that was the advantage of this. So right now we have satellite in for search and rescue operations, communication during disaster, and telemedicine network. And rest all other communication need we are trying to give to private, we are trying to give our technology, whoever is interested, and put the satellites in orbit to run the communication. So now the requirement is then you have to integrate all this communication infrastructure. Your mobile should be integrated with LEO. LEO should be LEO satellite. LEO satellite should be integrated with geostationary satellite, and all these are going to happen in the next. And next is satellite navigation. This is also another thing which is actually regularly, knowingly or unknowingly 80% of our work, daily work, is dependent on satellite navigation. Whether you are going somewhere, whether you are trying to locate something, or you are having it you are trying to deliver something somewhere, everywhere you are using this satellite navigation. Now, because students are here, so I just thought I will give a little theory of it, but it's very, very basic and very preliminary. See, you have 3 objects in sky, and suppose, and you know their exact location and time. Now, you want to locate something on Earth. So, normally by distance calculation, if user, can I get it? Okay. If the user is sitting on Earth and you have 3 satellites, you can always calculate the distance. And if you have 3 satellites, you get 3 equations, and from there you solve it. So, you get the location of the person who is sitting on Earth. Now, that is the way, but it's not that simple. You need a very perfect time standard. You need to take all other things into account. It's a good computational effort. So, now, but this way we can have the communication satellite, and our Navik is like that. And we have in geostationary orbit this communication satellite infrastructure. But you know about already GPS, then Galileo, Vido, GLONASS. Everybody has gone for it, and they are all on middle Earth orbit. So this is about Navik. Now, Navik application, if you see, safety of life, transportation, and location-based services, and timing synchronization. You know why it is important? Suppose you have a lot of power grids, and you want to combine them and give a service to service somewhere. Now, power grids need to be synchronized. If they are not synchronized, you will unnecessarily get shut down of them, and if you will be not able to control that. That Navik is used also for that. Now, these are the 2 part I have covered, that is communication and navigation. Now, why I am covering this? I am coming to your, probably you all are excited about Chandrayaan 3 and the planetary exploration. But these are the basic technologies what will be needed to all these things, and we learned all this technology in this journey. So, can you go to the next? I'll give you a glimpse of these technologies. So, it starts with a small wafer. We make semiconductor devices. From there, we design the integrated circuit. The integrated circuits, we combine them to make a subsystem. Now, those subsystems are put in as a satellite. You see, it's a box-like structure, and these subsystems will be inside them. And then, whatever data we get from that, we use for different application. The whole chain is a huge. So, what you normally see is the fanfare, but this is the hard work behind that. So, can you put the next? The next is I am going to talk about remote sensing satellite. Now, why it is important? Even if you are going to a planetary systems, see, either you can land there, get in situ measurement, or you can rotate around that and get all the remote sensing images from that, and from there you get a image of Earth. You can map image of Mars or Moon. You can get the feature mineralogy of that. All these things you can explore from there. But we started with Earth's exploration. You know why it is? Because we wanted to see that, it all started with, I think, coconut wilt disease. That is, in Kerala, coconuts were getting disease. So then Professor Pisarotty, he started this to help the farmer. And after that, we continued that. We made many satellites which are used to help the farmers and the fishermen and all these and common men. Now, there are two ways to get the remote sensing. One is, okay, you image it. You have camera on Earth, on the satellite, and image it. Now, after image, what you get is that you can analyze that image, and from there you can get all the information. Another way is that you can put a active remote sensing, where you are transmitting something to Earth, and whatever is the reflection, you are getting it, and from there you are trying to do the remote sensing. Now, this in remote sensing, we have optical remote sensing and microwave remote sensing. Can I go to the next? Now, what you see here is again the technology behind it. Okay, you need not understand it at this moment, but why I put this slide is the reason that you need to make the telescopes, you need to make the corresponding optics, you need to make the detectors, and from there you can take the picture. And we started with a 1 kilometer resolution, and today we are in 0.3 meter resolution. So this is the way it has advanced. Now, once on the way you get all these technologies in your hand, what you do with this, what we did with these technologies. Now, there are two examples I have shown, but there are many examples. Next, yes, stay here. So there are many examples, but I took specifically two examples for a reason. See, suppose we are talking about fishermen. Now, what their problem is, let us think. So he needs to know that where fishes will be available on the sea, so that he can go there. So we have remote sensing satellite, which will sense the sea surface temperature and chlorophyll content on that area, and from there it will tell that, okay, you may get fishes at this zone. Now, when he has ventured out in the outer sea, now after that what? He doesn't have any communication network, so we have to provide him communication. Now, that is the role of communication satellite. Now, there is a ocean hazard. There may be weather problems. So we have to warn them that, okay, please come back now, don't stay at sea. So this is the way all the space infrastructure till now, whatever I told you, is useful to common man. And another is water conservation. And now all of you are knowing about the Sustainable Development Goal of UN. One is water conservation and management. Why it is necessary? It is very much necessary as for the survival of mankind. Now you have all the glaciers, you have rivers, you have dams. Now you have to monitor them regularly. We have to know that where we are doing the mistake and where you need correction. So these all are important work what satellites were doing. Can I go to the next? Yes. Now you see, it's all what I told you. It all started with vision and mission of ISRO. What Dr. Vikram Sarabhai saw. We must be second to none in the application of advanced technologies to the real problem of man and society. So that's what we did till now. Now, once we have mastered these technologies, next logical extension can be, okay, why not to go for planetary exploration? So now our vision is harness, sustain and augment the technology for national development while pursuing the space science and research and planetary exploration. So that's what the way we went now. Now, planetary exploration and the exploration of the universe, you can do two ways. One is we can go there and sit and see what is happening. Any Kus is going to talk to you about that human space program, what we are doing about it. And another is we can go there, we can put robotic missions, we can put lander, we can get the in situ measurement and then analyze it and send the data to Earth again. And we can put orbiter, which will image that planet and give us all this data. So I'll just briefly tell about our planetary exploration journey. Next. Yes, it all started with Chandrayaan-1. So in 22nd October 2008, we had Chandrayaan-1, the first mission, lunar mission. Now, what we have put a moon impact probe also there, and I think it was a brainchild of Dr. APJ Abdul Kalam, that he suggested this and ISRO accepted it immediately. So we were imaging moon at different bands. We had orbiter. Now, lunar tectonic activity, that how it is working, we tried to sense from the Chandrayaan-1. But later we will see that in Chandrayaan-3, actually we got the lunar seismic activity also recorded. So, and our next was Mars orbiter mission. And that also was a huge success, all of you may be remembering. And that also was imaging, we have a Mars orbiter, and it was 750 kilometer by 71,000 kilometer it was moving. And it was imaging Mars when it is coming close to Mars, and Martian geology it studied. We have an excellent Mars atlas, that is, I think that's a interesting part of it, like we see globe today, our Earth. That way we prepared an atlas for Mars, and that's an emerging atlas. You can see probably it will be available in ISRO site. And then imaging moons of Mars, that is Deimos and Phobos. This is what was done with Mars orbiter. Then we had AstroSat mission. AstroSat is actually imaging galaxies and black holes. We did it on ultraviolet and X-ray band. Now, what our scientists are very well, we made the instrument and we have put them in space, and scientists are very much interested to get this result, to see in the galaxies and black hole in how is X-ray image looking and what they can infer from that. And probably we are going to put another AstroSat mission. And then Chandrayaan-2 was there. Chandrayaan-2 is actually very less talked, I will say, maybe for wrong reasons. It had a lander, but okay, that time it didn't succeed, but it had a 0.32 meter resolution orbiter at 100 kilometer, and that is the best resolution imaging of moon you can get till today, and from any country, it's best among all the countries of the world. Now, Chandrayaan-3, I thought, okay, I will not talk about this because you have heard enough of it. But Maharaji suggested, no, we should cover that. So I'll come to that later, that what we have learned from Chandrayaan-3 and what has come when it is landed there and when it is working there. Then we have Aditya L1 mission, which has started its journey. It will reach by January 2024. Now, this is for studying solar atmosphere, chromosphere and corona with remote sensing and in situ. Now, we know about solar storms. Now, solar storms actually affecting Earth. It affects the communication, it affects many more things. So, scientists wanted to study that what is the origin and how it is reaching to Earth. So, for that it was made. It has got a lot of payloads, that is, which will be, as a orbiter, he will take the images, and something which will be coming out of sun, it will analyze them also. Oh, sorry. Okay. Can you go to the next? Now, once we make all this, okay, when I am trying to cover Chandrayaan-3, if you know the objective of Chandrayaan-3, okay, it is just the payloads, whatever is listed. Okay, payloads probably you have heard about them, but I will show you the results. Come to the next one. Yes. Now, Chandrayaan's temperature, temperature on the moon surface and underneath the ground and the above certain height, how the temperature profile looks. I don't know whether you are able to make it or not. I don't have it. So I'll come here. So in the x-axis, what you see is the temperature, and y-axis is the depth. At what depth, what temperature it has recorded. And then what are the minerals available on a lunar surface? What are the elements available in the lunar surface? See, you see, this is one of the leaves the payload, whatever was there in the rover, what it has done, it has taken the sample and it has analyzed it, and it has given all these spikes, whatever you are seeing, the element names are also there. For initially it got, it detected sulfur, and then all other elements like chromium and ferrous material also. So this is the learning from in situ measurements, whatever has happened there. Can you go to the next? Yes, right side what you are seeing is like Earth, we have earthquake. This is also a natural event recorded by one of the rover instrument, that okay, it is a moonquake, and the amplitude and duration of this what it is recorded, and it is near the lunar surface. You have plasma. Now plasma, how, and it is due to electron also or due to ion also. How is the current? What is the concentration of that? That also it has sent. So these are the scientific measurements till now shared. So these are not very, means these may not be very much interesting, or okay, for scientists definitely it is very much interesting, but you may not find the immediate application of that. But these will be probably future roadmap for exploring further, and if we are able to get some useful mineral at the lunar surface. Can you go to the next? Yes. Now, when you made all this space infrastructure, you have put all of them, that satellites around the moon, Mars, maybe sometimes you may go to Saturn, moon also, Venus. Now we have to keep communicating with them. You have put a rover, but you need to get the data from that. This is our deep space network. It is near Bangalore. It is Belur. And what you are seeing here is a big 32-meter dish antenna, and it has got very low noise Messer amplifier, and that is because whatever is coming is very, very weak signal. So from there you have to generate, you have to see the data. So that is what it is doing. And these all subsystems are there, and this is actually keeping a record of our deep space observation data also. Can you go to the next? Yes. Now next is the payoff. What we have gained doing all these things. So I have shown you few of the scientific results. So science, it is advancement of science and technology for humanity about outer space. Now, okay, if you see today direct application, probably it will not be there, but I'll quote Vivekananda ji from here, Swami ji. See, what he felt, knowledge should be, knowledge is for its own sake. It is not necessary that always it has to be useful. Knowledge itself is greatest reward. So that is one part of it, but I am not telling only that. Let us look at the economic benefits also. So do you know, probably you might have seen in print media that it has actually given greater visibility of our industries who have contributed to the space programs on those missions. Now, and if you are familiar with stock market, probably you will see, I will not name it, but all the share prices of those who have contributed has increased significantly. Now, this is economic benefit. Now, there is a greater benefit. The greater benefit is demonstrating our capabilities and getting our confidence. Whenever you have any such mission, what you gain is the confidence and faith of yourself and the world. You know, we were in British colonies for several, around 150 years or more. What was the greatest thing we lost there is our self-confidence. And that is where Vivekananda, Swamiji has struck us hard. That, okay, you get your confidence back, rest, everything will follow. So these are the missions where we can tell, where we can see that, okay, we can also do it, and we can do it much better than others. So this is actually, and another thing you see, that unity of India is a very, very diverse country. There are a lot of opinions, But about two things they will be always united. One is the spirituality and another is the space exploration. So whenever you have some success, we have seen the enthusiasm in the people and we have seen the unity of nation, how it has happened. So this is one of the greatest thing I will tell has happened. Now, what I was talking about, the colonialism and what was the state of India that time. Now, somebody has commented that the greatest loss we had is not the loss of Kohinoor diamond. It's the loss of our self-confidence. So these all missions give us back that. In fact, any success gives us back that. And it's like, if you remember about, and everybody will be, Swamiji's story of the lion cub who was raised among the sheep. So it was thinking that it was a sheep, and it was behaving like that. Then one lion one day saw it, and he stalked on him, and then caught him and brought him. What are you doing? You are not a sheep. He told, no, I am a sheep. Please leave me alone. Then he told, okay, you come with me. He came to the water and showed him the reflection, and you and I are the same. So that was the turning point for him. He also realized that he is a lion. He is the Vedanta Keshari. What I was seeing a lot of lions near Vivekananda's statue, so that also reminded me that. Now, these all successes give you a mirror to see yourself and get the self-confidence. So that's the I'll say that is the greatest benefit of all these missions. Now, I'll share something about what's so special about ISRO, that ISRO is able to take up these all missions. One is definitely the vision of all our earlier luminaries, I will say. Vikram Sarabhai, when he saw that space program is necessary for India, and he did not go for competition. And today also we are very sure that we are not in competition. This is a logical extension of our work, that whatever we have done till now, what we can do out of it, and what we can learn more than that. So that's the vision. And the winning spirit. So it is an emerging spirit. Actually, space is very, very unforgiving. So if you do any mistake, you know what happened in Chandrayaan-2 lander. But ISRO was never deterred by that. It has learned from it. It has come back with double vigor and made all the things, studied all the things carefully, then made all the required changes, and then gone with a better confidence. And next time it was a definite success. So that's the spirit. In fact, this spirit actually, Dr. APJ Kalam also once told about Vikram Sarabhai. When they were working in lab throughout night and something they did that did not work. So finally all were very much upset that what to do about that. But what Kalam Sahib tells, okay, Vikram Sarabhai came and it's like a new lease of life. Okay, nothing has happened, so go ahead. So that was the mentality. So that's what it is. So we don't see that, okay, whatever something is filled, there is always to learn something from there, and if you are sincere, definitely you will succeed. So that's the message. You remember our Thomas Alva Edison? I have not failed 10,000 times. I have learned that how those 10,000 methods doesn't work. So learning is always like that. Now, can you go to the next? Yes. Now I will talk about something where we are going. Okay, we have missions further. We have Astrosat missions probably will be planned now. We may have a Venus mission also, and we may have a moon sample return. You know, till now we have landed there, but we have not got anything returned from there. So that is also as a thought, and that is a Mars robotic mission. These all things can be done, and we are not far from this as far as the technology is concerned. But it depends that, okay, whether we will get world collaboration in this. Because one thing I was talking to people that, okay, probably now everybody, you see that in USA has got a lunar mission manned lunar mission long before, and since last 50 years they didn't have anything. The reason is that okay, during the space race, during the Cold War, you took all these decisions. But when that is not existing, then you always question that what benefit we are going to get out of it. So you normally concentrate on the public benefit. Now, once you want to do it, outer planet exploration, it should not be one nation affair. Now, if it is not one nation affair, then who is going to collaborate with you? If you have the technologies, people will come and collaborate with you. And it happened. It happened when you had the synthetic aperture radar technology in NASA, NASA has collaborated with us. Likewise, we have now handled on all our lander and these type of missions. Now people will collaborate, and we are expecting a collaborative missions, because these missions are going to benefit humanity. These are not a single, it is not a benefit for India alone. So that is one part of it. And let us see what new physics and new technologies are going to come. So if we start with gravitation, it gives us many things, Newton's gravitation. It gives us power to land on some planet or orbit some planet. Then 1905, the relativity came. We came to know about the mass energy equivalence, and it released the atomic power. And the power inside the atom, which we can, okay, which way we can use it, that's up to you. But it gave us that hand. Next came quantum physics, and it pervaded our life almost. Whatever you are doing today, starting from your mobile to all the gadgets, whatever you are seeing, we are actually indebted to quantum physics, and it has given us solid-state devices on all of them. So beyond now, quantum physics, now the problem comes where, you see, when you try to make quantum physics and gravitation together. Now, I'll tell, if you are interested in this part of it, you just look at a lecture of Nima Arkani Hamed of Institute of Advanced Studies, Princeton. What he told is a very simple thing. I just looked at the lecture. See, suppose you want to combine space-time and gravitation. Now, quantum theory, what happens? Because of uncertainty theory, what happens if you want to look into a small object? We use normally a microscope, so it can resolve up to the frequency of light. Now, beyond that, we go to electron microscope. Now, electron microscope also gets into certain up to, say, angstrom level. Now, if you want to go beyond, no, just go back. If you want to go below that what you can do? That is, okay, you cannot do anything. You have to do a thought experiment. Now, if you are trying to see something which is very, very minute, of the order of Planck scale, that is 10 to the power minus 35 meter scale, what happens? You make a light to see it. The frequency of light is such that energy will be very high, and the energy will be so high, according to Einstein's equation of E equal to mc square, it will, and the theories over that, you will land up in a black hole. So what he meant to say, that below 10 to the power minus 35 centimeter, space-time actually loses its significance. You cannot use space-time. So reality, which we are all knowing depending on space-time, it suddenly becomes fuzzy. So this is probably where science and spirituality meet. Now, new science, whatever, go to the next. Now, there is a strange fact in quantum mechanics, what is called is entanglement and superposition. That is what we are saying. You don't see anything, whatever you are trying to measure, you cannot do it. Before your measurement, the state was not certain. And two particles can be entangled, so that one, if you try to measure, other one will be getting affected. And these two, actually, why I am talking about this? These two we are trying to use in our communication. Our next secure communication is going to be with these two properties of quantum physics. So And this here again the reality becomes very fuzzy, because whatever we thought that everything is certain mass, energy and momentum of something which is certain, which suddenly is disappearing. So with this, I just try to share that with this we are trying to do some new technology. We are trying to do a new communication method which will make the communication secure. Now you have a lot of cyber frauds and all these things, so that probably we will be able to prevent using this technology. Now, next part probably I'll tell, okay, if you have a little time, or I don't know whether I have exceeded the time. 5 minutes. Okay, okay. So, now I talked about quantum reality. Now we are seeing the reality and matter is disappearing before our very eyes. And if you see that what we can do is about matter is not there. Anything in any science start with some axioms. It start with our sense organs, and everything has limitation. You can make questions that whether they are valid or not. But there is one thing you cannot question. Can you tell what it is? It's your very existence. So from there, if we can start the science and boot up space-time and the particle, so probably that will be the very new direction where spirituality and science will meet. And this is what I think Swamiji told, that science will and spirituality will shake hands sometime. So probably we are approaching that time now. With the new science, we are looking ahead to that. And what we try to strive is, it's Swamiji's vision that, okay, we need to be self-reliant, we need to have confidence on us. So because of that only we could go this far. So again, Pranam Swamiji, Thakurma and Ma Saroda. Thank you. Thank you. It was really wonderful to be here. So thank you, Nikhileswaranji, for inviting me to have interaction with these young minds.